So last time we talked about the derivative of a function at x equals a, and we provided the definition of a derivative, which is given by this particular thing here. And just a reminder, what the derivative here is talking about is one of three possible things. We call it the derivative at a point. It is also the instantaneous rate of change at that point, and also it is the slope of the tangent line at that point. So all three of these are equivalent. They are the same. And just to do a quick example to show the concept here, if we were to think about the function f of x equals 1/2 x squared, and I want to figure out what the derivative is at x equals 2. Well, that's going to be the same thing as the instantaneous rate of change, or the slope of the tangent line at x equals a, or x equals 2 in this particular case. So a tangent line is just the line that touches the graph at that point. And if you were to calculate the slope, notice that we have a run of 1 and we have a rise of 2. That means that the slope of that line is 2. So the instantaneous rate of change, or the derivative at that point, is 2. Now today, we're going to consider another notion of a derivative, and that is going to be considering the derivative of f of x as a function. So the way that this is defined is that we define it pretty similarly, except instead of using an a, where there is, we're trying to find the derivative at a point, we're going to use an x, okay? And what this is going to do is that this is going to give us some function that basically gives us the slope of the tangent line at any given point. So just to illustrate, if we go back and we look at our function y equals 1/2 x squared, and we consider the slope of the tangent line at two different points. So here we have x equals 2, and at this particular point we have x equals 1, and I say, well, what's the slope of the tangent line at x equals 2? Well, we just figured that out. That's going to be 2, so the derivative at that point is 2. But if we consider the slope of the tangent line for the at x equals 1, you'll notice that if we go over 1, we're going to go from 1/2 to 3/2. So the rise is 1, which means that the slope of that line is going to be equal to 1. And without going into the details on how we know this is true, we can actually conclude that the derivative as a function is going to be x. So that means if I want to find the derivative at any given point, so if I want to figure out, well, what's f prime of 5, well, the slope of the tangent line at x equals 5, somewhere up here, is going to end up being 5. The notation that we've used for the derivative so far is this f prime notation. And it turns out that because calculus was invented by both Newton and Leibniz, different mathematicians ended up using different notations, so oftentimes we will interchange the two, so we should become familiar with the two. Again, the derivative can be thought of as a function and also at a point. As a function, we call it f prime of x, which is this difference quotient here with an x plugged in, and then here we just consider an a. And again, the difference between the two here is that when we consider the derivative at a point, we're specifically fixing a point, so x equals 2, x equals 3, but over here, when we deal with it as a function, we're considering any possible point, and then we can plug that in at a later point in time. So they do look the same, but we're talking about different concepts here. So what are the different notations? Well, the first one we've seen is f prime of x. We can also use y prime, and that's what we do when we consider the derivative as a function. At a point, all we have to do is plug in a. or whatever that point is. So let's say a was equal to 3, we could plug in 3 there, and that would work. So f prime of 3, y prime of 3, that gives us the derivative at a point. And this notation is attributed to the mathematician Lagrange. We also have this notation, which the way that we say this notation here is dy dx. So dy dx. It's not dy divided by dx, or we can say that this is d dx of f of x. When we notate that at a point, it's a little bit different because we don't actually plug in the a. We draw this vertical line here, and then we put whatever the point is. Again, x equals a. That a is a placeholder for whatever number we decide to plug in. And this is attributed to Leibniz, one of the co-founders of calculus. I would say that these two notations are the ones that are going to be most commonly used in a calculus class, but when you get into engineering and some other fields, you might see different notations, such as Euler's notation. He just uses df or dy of x, and you can just plug in a like we did with Lagrange's notation. This is attributed to Euler. And then lastly, we have Newton's notation, and he uses dot notation. So he will use something like y dot. And Newton's notation is specifically going to be an indication of a time derivative. So when you see a y dot, you can think of this as the same thing as a dy dt. We're taking a derivative with respect to time. And again, at a point, we can use y prime of a. And as I was saying, that was attributed to Isaac Newton, one of the other co-founders of calculus. Again, these notations at the top are probably the most common that I'm going to use. I probably won't even use the other two in this class, but I'm just stating it for familiarity. Anyway, that's it for this section. I hope you found this video helpful, and as always, take care.